Welcome to the fourth part of Elements of Neural Network and Deep Learning. I am Tinya B. Ganesh. Like my earlier presentations, this presentation is also based on the following two courses from Coursera: Neural Networks and Deep Learning Specialization by Professor Andrew Ng, and Neural Networks for Machine Learning by Professor Jeffrey Hinton at Coursera, and the two books, Neural Network and Deep Learning by Michael Nielsen, and Deep Learning book by Ian Goodfellow, Yoshua Bengio, and Aaron Corville. I've also used other material from the internet. In our third presentation, I had shown a simple three-layer network where we had the input layer x1, x2, x3. You could have any number of inputs and a bias B, and we had an output layer, and between the input and output layer we have the hidden layer. The hidden layer, these circles are called activation units, and these activation units could be any non-linear function. For example, we could have the sigmoid function, tanh function, ReLU function, or Leakey ReLU, or any other function. And if you're going for a binary classification, the output activation unit is always a sigmoid. Now, there can be any number of hidden layers between the input layer and output layer. If you have more than one hidden layer, then it's called a deep learning network, and there can be many units in each hidden layer. Each hidden layer could have any number of activation units. Here are two simple neural networks. In our first case, we have a two-layer neural network. In fact, this is what I had shown in my second presentation, where I had used a neural network to simulate a logistic regression. So we have an input layer and output layer. However, and in the third presentation, I had shown one input layer, one output layer, and one hidden layer as a three-layer. However, there is another convention where the input layer is not considered in counting the number of layers. So here we just have one layer, so this is called a one-layer neural network, and here we have hidden layer and output layer, so it's called a two-layer neural network. However, I'll be using the convention where I also count the input layer as a layer of the neural network. Now, in our third presentation, I had shown how the neural network works. What is the basic mechanism behind it? We have a set of weights and we have a set of input features, and we have hidden layers and an output layer, and for a particular set of weights we get a particular output and loss associated with the output. Loss is basically the error in the output. By changing these weights, you can change the output and also change the loss. Now, the intention of the neural network is how we can choose the weights in the input layer and as a result minimize the loss at the output layer. And this is done by a process known as gradient descent, where we change the weights by a factor where alpha is the learning rate, and we compute the gradient of the loss versus the weight, and we change the weight by this particular factor. We compute the gradient and then we subtract the weight from with the learning rate, and similarly the bias we change with this particular gradient and the learning rate. So the neural network goes through a series of cycles where we do a forward propagation step, we compute the cost, and then we do a backward propagation, we compute the gradients, and then we adjust the weights and we compute the cost. Similarly, we do a forward propagation, compute the loss, we do a backward propagation where we compute the gradients, and then we change the weights correspondingly, and we do this iteratively. And if we choose an appropriate learning rate, then this cost will keep dropping and decreasing, and it will subsequently reach a point where it cannot decrease further, or decrease very slowly, and at that point we stop, and that set of weights is the optimal set of weights for which the loss is minimum. However, I must admit that we have to choose the learning rate appropriately, because too small a learning rate can cause the decrease to be very slow, and if we choose too large a learning rate, then it can oscillate between the cost increasing and decreasing. Now in our previous presentation 3, I had taken a simple 3-layer neural network where I had the features x1 and x2 and a bias b1, and we had the weights w11, w12 and w13, where the superscript is the weights correspond to layer 1, and we can compute the linear activation z11 as the product of w11 into the feature x1 plus w21 into x2 plus the bias, which is what we have here. Similarly, z12 is w12 superscript 1 x1, w22 superscript x1 x2, x2 plus b1, and z13 is w13 superscript 1 x1 plus w23 superscript 1 x2 plus b1. And then we compute the activations. In the previous position, I had chosen tan h as the activation. So A11 is tan h z11, A12 is tan h z12, A13 is tan h z13. And then we compute the linear activation at the output layer, the z21, which is again the product of the weights and the activation of this layer. So it's A11 W2 superscript 211 plus W21 superscript 2 A12 plus W31 superscript 2 A13 plus B2. And then since we're using binary classification, we use A21 equal to sigmoid of Z21. Now we can represent all these equations in the matrix form, which is very convenient. So Z11 is a vector of Z11, Z12 and Z13, and we can write the weight as a weight matrix multiplied by the feature matrix. And A11 is again a vector of A11, A12, A13, and we write the vector of the activation functions. Similarly, Z2 is a product of this vector into this weight vector into this linear activation function plus bias, and the activation layer 2 is the sigmoid of Z21, which is basically, I've just rewritten whatever is on this particular page in matrix form. Now I can further shorten this, where I can have this Z1, which is a vector of Z11, Z12, Z13, and W1 is our weight matrix, which we have here, and X is our input vector plus B1. So here the capital letters denote either a matrix or a vector, and we can just simplify it in the shortened form. So this is the forward propagation step. And the backward propagation step, as I said, we have to compute the gradients. The whole point about neural network is we have to identify how the loss in the output layer is affected by small changes in the weights in each of the subsequent layers. And once we know this particular how this loss is affected, we can use gradient descent to adjust these weights, and if we follow this process iteratively, we will it will give us the set of optimum weights which will result in the lowest or the minimum loss. So for a sigmoid output activation unit, we know the losses already we have seen in presentation 2 is given by minus capital Y log of A2 minus 1 minus Y log of 1 minus A2. And as I said, we are interested in computing dl by dw2 and dl by db2, and also dl by dw1 and dl by db1. So we have already seen this equation. Just quickly recap. This is just for recap. dl by dz2 using the chain rule is dl by da2 and da2 by dz2, and dl by da2, given that this is the loss function, it is the derivative of that is 1 minus y by a2 plus 1 minus y divided by 1 minus a2, and the derivative of the sigmoid function we have already seen it in presentation 2 is a2 into 1 minus a2, and in our presentation 2 for the sigmoid function sigma, it was sigma into 1 minus sigma, and if we multiply and reduce this, it will come to a2 minus y. Similarly, dl by dw2, again using the chain rule, it's dl by da2, da2 by dz2 and dz2 divided by dou w2. Now we have already computed this term above, so it is just a2 minus dou z2 by dou w2, which will be a1, because z2 is equal to dou z2 by by dou W2 is A1. So that's what you get here. Similarly, dou L by dou B2 is again using dou L by dou A2, dou A2 by dou Z2, and dou Z2 by dou B2. This we know is already A2 minus Y, and dou Z2 by dou B2 is actually 1. So it is just this. Similarly, dou L by dou Z1, again you just have to go through the step of writing this as a chain rule. And if you see the computation graph which I had given in presentation 2 and presentation 1, you can easily see how this all works out. You will finally this amounts to basically dou L by dou A2, dou A2 by dou Z2. So dou L by dou Z2 we already seen this A2 minus Y, and dou Z2 by dou A1 is W2, and dou A1 by dou Z1 is the derivative of the tan H function, which is 1 minus A1 square, and dou L by dou W1 is basically all that we saw up to Z1, and addition dou Z1 by dou W1. So we just add all these factors which are there terms, and then dou Z1 by dou W1 is X, and dou L by dou B1 is again this whole set of terms, and dou Z1 by dou B1 which will become which is just 1. So these are a set of equations for a 3-layer neural network. And once we have, as I said, the two key things we are interested in backpropagation is to find how the loss varies for a change in the weights in layer 2 and layer 1. And after we compute this how the gradient of the loss with respect to weights W1 and W2, B1 and B2, we can compute the weights iteratively using gradient descent, and we follow this process and compute the cost and for each cycle of the gradient descent, and this will result if we have chosen the correct learning rate, it will keep on decreasing. Now let us go to the next step where we take a 4-layer neural network, and the whole intent of this is how do we derive the equations of a L-layer neural network, or in other words we want to derive all the equations for a multi-layer multi-unit neural network. So we can do this by taking a 4-layer neural network where we have the inputs x1 up to xi and a bias term. We have the first layer z1, and this is the input layer, this is the output layer, and we have two hidden layers. So z1 is the linear activation. Then we have the first activation unit, which could be any activation unit, tan H or ReLU or leaky ReLU. Similarly, we have the second linear activation unit, and the second activation unit which could be again tan H ReLU or leaky ReLU or a sigmoid, and the third. And finally we compute the loss, assuming it's a binary classification, we'll be using a sigmoid function at the output. So we can just like in the earlier section, as you have seen here, we can write the equation for the forward propagation. Z1 is equal to W1 A0. A0 is actually the input, which could be X in our case, or X is also referred to as the first layer A0, W1 A0 plus B1, and the activation is A1 is equal to some function, it could be any function, ReLU, tan H, sigmoid or leaky ReLU. Similarly, Z2 is equal to W2 A1 plus B2, and A2 is equal to some function, activation function G of Z2, and Z3 is equal to the weight matrix at this layer into A2 plus B3 plus A3 is the sigmoid. Assuming this is a binary classification problem, we use G of Z3. Now similarly we will compute all the equations for this backward propagation. Here this is the equation of the forward propagation. For the backward propagation, it will be at the final layer, since we have a sigmoid unit. We have seen for the loss for a sigmoid unit is minus y of log A3 minus 1 minus y log of 1 minus a3. So dou L by dou a3, taking the derivative of this, we have already seen this. We have in presentation 2 and 3, it's minus y of a3 plus 1 minus y 1 minus a3, and dou a3 by dou z3 for a sigmoid function, it is a3 into 1 minus a3, because if we have sigma of z is equal to 1 by 1 plus e power minus z, then dou sigma by dou z is equal to sigma into 1 minus sigma, so it is this. So dou L by dou z3 is equal to basically dou L by dou a3, which is this, into dou a3 by dou z3. So if we multiply these two, we have already seen it will reduce to a3 minus y. Now dou L by dou a2 is dou L by dou z3 into dou z3 by dou a2. So dou L by dou z3 we already seen, it's a3 minus y, and dou z3 by dou a2 is equal to w2. Dou z3 by dou a2 is w3 by looking at this equation. Now because now dou L by dou z2 is dou L by dou a2 by dou z2. Now dou L by dou a2, we have seen it as the above equation, a3 minus y into w3, and dou a2 by dou z2, this is the second activation function. As I said, this activation function could be anything. We could choose depending upon what we decide, whether we want it to be a tan H, we want a ReLU or a leaky ReLU or a sigmoid, we could choose. And so assuming it's just some function g of z2, we just take this as the derivative, we just write as g of z2 just for a generalized purpose, because we do not want to make it either this or that, just we want to make it general. Now dou L by dou w2 is equal to dou L by okay, this is basically, I'm just showing dou L by dou w2 is equal to dou L by dou z2 by dou z2 by dou w2, and dou z2 by dou w2 is a1, so dou L by dou w2 is equal to dou z2 into a1, and dou L by dou b2 is equal to dou L by dou z2 into dou z2 by dou b2, but since this is 1, I just write as dou L by dou z2. Now similarly, dou L by dou a1 is dou L by dou z2 into dou z2 by dou a1, and so we leave this as it is, and dou z2 by dou a1 is w2, and dou L by dou z1 is equal to dou L by dou a1 and dou L by dou z1 is dou L by dou a1 by dou z1. So this is dou L by dou a1 is basically dou L by this particular factor, and then this one is just the derivative of that, and dou L by dou w1 is dou L by dou z1 into a0, and dou L by dou b1 is dou L by dou z1. And if we look at these two sets of equations, then we can write this generalized form. Basically dou L by if you look at this, dou L by dou a1 is equal to dou L by dou z2 into w2. So dou L, wherever it is they have the subscript for the layer, we just use L for that, make it generalized. So dou L by dou AL is equal to dou L by dou Z L plus 1 into W of L plus 1, and dou L by dou Z1 is equal to dou L by dou AL, and this is basically dou A1 dou Z1. This could be any activation function g of Z, and so when I take the derivative, it becomes g dash of ZL, and dou L by dou W1 is equal to dou L by dou Z1 into A0. So again I just substitute L for wherever it is numerically. So dou L by dou WL is equal to dou L by dou ZL into A into L minus 1, and dou L by dou BL is dou L by dou ZL. So these are the set of generalized equations. Now we can so basically this is exactly what we are trying to do. We have either we have the input features, which is also called A0, and we have a weight matrix. Let's say this for the first layer W1 and the bias is B1. From this we compute the linear actuation Z1, and also after we compute that, we also compute the actuation, whichever actuation function you use, sigmoid or tanh or ReLU, and we pass it to the second let us say module, which has another weight matrix that layer W2 and bias B2, and from this we compute Z2 and the actuation A2, where A could be any actuation function, and so on we could have in the forward propagation direction. And finally at the last layer we'll have the loss, and from the loss we can compute how the loss varies for dA2, and from that we can compute how the loss varies for dZ2, and also compute dou L by dou the weights in the second layer, and dou L by dou B2, and then we feed this into this first module once we compute this, and from here again we will get the loss with respect to the weights in the first layer and weights and the bias in the first layer. So basically if you follow this process of forward propagation, backward propagation, we will be able to compute the gradients for the weight matrix and the bias in each of the layers in the backward direction, and we'll use those weights and biases to do the gradient descent across each of these layers. And at the end of the backward propagation cycle we will compute the cost, and we will again get a new set of weights, and we'll use this new set of weights to do a forward propagation, and in the next cycle we will do a backward propagation, and we will continue the cycle till our cost it reaches a minimum. So these are the L layer equations. ZL is equal to the weight matrix in the layer L into the actuation in the previous layer plus the bias, and the actuation Lth layer is the actuation function, which could be a ReLU or a tanh or a sigmoid or a leaky ReLU, into the inner actuation ZL. And we have the backward propagation dou L by dou AL is dou L by dou ZL plus 1 into WL plus 1. Dou L by dou ZL is equal to dou L by dou AL into the derivative of the actuation function at that layer, and dou L by dou WL is dou L by dou ZL into AL minus 1, and dou L by dou BL is dou L by dou ZL. So with this I have constructed shown the equations of a multi-layer multi-unit deep learning network, and when I implemented this I implemented in Python, R and Octave. So just to make the problem more interesting, I used the equation of a lemniscate of Bernoulli and plotted the lemniscate. So basically all the points within this lemniscate are a 0, and all the points outside are a 1. And then I used my multi-layer L-layer deep learning network to learn this fairly complex non-linear pattern, and this is what I got. This is the boundary which I got in Python. This is the boundary in R, and this is the boundary in Octave. Just a point I would like to mention. Of course you may think that this is not that good, or I mean this looks a little better and all, but the whole point is you can get it to be as good as possible, but you need to spend a fair amount of time in choosing the right hyperparameters, the learning rate, and the number of hidden layers, and the number of hidden units per hidden layer. So it's a combination of multiple things. So if you make the appropriate choice, then you can get it starts to work out very well, and the weights start to drop fairly fast. Thank you. So this ends the fourth presentation in elements of neural network and deep learning. Thank you.